Hi, everybody. It's Professor Mitchell, continuing with Chapter 2. Today, we're looking at Section 2.3 on arithmetic operations on matrices. In this section, we will define a matrix, talk about column, row, and square matrices, addition and subtraction of matrices, multiplying a row matrix and a column matrix, matrix multiplication, the identity matrix, and the matrix equation. So a matrix is any rectangular array of numbers and may be of any size. The size of a matrix is n by k, where n is the number of rows and k is the number of columns. The entry a sub ij refers to the number in the ith row and jth column of the matrix. Two matrices are equal, provided that they have the same size and that all their corresponding entries are equal. So for example, here you see a 2 by 3 matrix. It has 2 rows and 3 columns. The entry a sub 1, 2 is the entry in the first row, second column, which is -1, this -1 here. The entry a sub 2, 3 is in the second row, third column. That would be this 7. These two matrices are equal. Notice that they have the same size and all the same entries. However, these two matrices are not equal because they're not the same size. A row matrix or row vector only has one row. A column matrix or column vector only has one column. A square matrix has the same number of rows as columns, so that's a pretty logical name for that. So this matrix is a 2 by 2 matrix, which makes it a square matrix. It has 2 rows and 2 columns. This matrix is a 1 by 4 matrix. It has 1 row and 4 columns, which makes it a row matrix. And this is a 3 by 1 matrix and a column matrix. It has 3 rows and 1 column. All right, that brings us to addition and subtraction of matrices. The sum A plus B of two matrices A and B is defined only if A and B are two matrices of the same size. In this case, A plus B is the matrix formed by adding the corresponding entries of A and B. Two matrices of the same size are subtracted by subtracting corresponding entries. All right, so here's an example. We can add these two matrices since they have the same size. So the first couple of entries in the sum of these two matrices would be 2 plus -1, which is 1, -1 plus 4, which is 3. And continuing on in that manner, you would get the matrix 1, 3, 10, 12, -3, -3. And then the difference of these two matrices would start out with 2 minus -1, which is 3, -1 minus 4, which is -5, and continuing, you get this matrix for the difference. This operation is undefined because these two matrices are not the same size, so the sum is undefined. All right, the next matrix operation we'll talk about is scalar multiplication. Given a matrix A and a real number C, the matrix CA is formed by multiplying each entry of A by the number C. So for example, given the matrix A, which is 2, -4, 0, 6, -2, 3, let's find the matrix 1/2 A. And I'll do that on the tablet. All right, so this is very easy. Just multiply every entry of this matrix by 1/2. So you get 1, -2, 0, 3, -1, and then 3 times 1/2 is 3/2. All right, that's all there is to it. So let's go back to the presentation. All right, now we get into matrix multiplication. So matrix multiplication is a little confusing at first. So we'll start by multiplying a row matrix by a column matrix. If A is a row matrix and B is a column matrix, then we can form the product A times B, provided that the two matrices have the same length. The product A times B is a 1-by-1 matrix obtained by multiplying corresponding entries of A and B and then forming the sum. If you've ever taken physics, this is the dot product. Remember that you can think of a row matrix and a column matrix as vectors. So the product of those two vectors is the same thing as the dot product in physics. All right, so here it is defined in general. It'll make a little more sense when we do it with actual examples. All right, so let's start with this matrix here. Okay, so to multiply this row vector by this column vector, or this row matrix by this column matrix, we're going to do 2 times -3 is -6. -1 times 2 is -2. 3 times 5 is 15. And then we're going to add those three numbers together. So it would be -6 plus -2 plus 15, which comes out to 7. All right, this one would be undefined because these two, this row matrix and this column matrix, do not have the same length. So you can't multiply these two matrices. All right, so we define matrix multiplication in terms of the product of a row matrix and a column matrix. If A is an M by N matrix and B is an N by Q matrix. So notice that the number of columns in A has to match the number of rows in B. That's the number N. Then we can form the product A times B. The product is an M by Q matrix whose entries are obtained by multiplying the rows of A by the columns of B, the way that we just described. The entry in the ith row and jth column of the product A times B is formed by multiplying the ith row of A and the jth column of B. All right, so I will illustrate that for you with this example. Let's go over to the tablet. Okay, so first let me point out that this is a 2-by-3 matrix. It has 2 rows and 3 columns. This is a 3-by-3 matrix. Since these inner two numbers match, that means the operation is defined, and the product is going to have 2 rows and 3 columns. All right, so let's talk about what that comes out to be. All right, so the 1-1 entry in the product matrix will be this row times this column. I believe that's the example we just did before. So 2 times -3 plus -1 times 2 plus 3 times 3 times 5, which comes out to 7. All right, the entry in the first row, second column will come from multiplying the first row by the second column. So that would be 2 times 2 is 4, plus -1 times 1, which is -1, plus 3 times 3. So 4 plus -1 is 3. 3 plus 9 is 12. Okay, hopefully this is making sense. We'll do one more and I'll show my work this time. All right, so the 1, 3 entry, that'll come from the first row times the third column. So this entry here will be 2 times 0 plus -1 times 2 plus 3 times -1. So what is that? That's 0 plus -2 is -2. -2 plus -3 is -5. All right, and then we do the same thing with the second row. So for example, the second row, first column, that's going to come from multiplying the second row by the first column. So that would be 3 times -3 plus 0 times 2 plus -2 times 5. So -9 plus 0 is -9. -9 plus -10 is -19. All right, and continuing in that manner, the second row, second column would be this row times this column. 3 times 2 is 6, plus 0 times 1 is still 6, plus -6 would be 0. And then finally, 3 times 0 is 0, plus 0 times 2 is still 0, plus -2 times -1 is 2. And that's how you multiply two matrices. Going back to the presentation. All right, so here they are walking you through it step by step. All right. Okay, so this example would be a 3 by 3 times a 2 by 3. However, that one's going to be undefined because, let me see if I can type it on here. Since this one is 3 by 3, and this one, whoops, and this one is 2 by 3, because the number of columns in this matrix does not match the number of rows in this matrix, that makes this operation undefined. Okay. All right, that brings us to the identity matrix. The identity matrix I sub n of size n is the n by n square matrix with all zeros except for ones down the upper left to lower right diagonal. So here are the identity matrices of sizes 2 and 3. I2 is this matrix 1, 0, 0, 1. I3 goes 1, 0, 0, 0, 1, 0, 0, 0, 1. So why is this called the identity matrix? Well, let's talk about what you would get if you multiplied these two matrices together. Notice that this one is 2 by 2 and this one is 2 by 3. So that operation is defined. The 1, 1 entry would be this row times this column. 1 times 2 is 2, plus 0 times 3 is still 2. 1 times -1 plus 0 times 0 is -1. 1 times 3 is 3. Plus 0 times -2 is still 3. All right, so the first row of the product matrix is 2, -1, 3. Continuing to the second row, you just get the same matrix back. Okay, so we have the same thing with real numbers. In real number multiplication, the number 1 is called the identity element for multiplication because when you multiply it by any number, you get the same number back. In order to do it this way, the identity matrix would have to be 3 by 3 in order for that product to be defined. And you can check, you get the same thing. Okay. So in general, for all n by n matrices A, I sub n times A is equal to A times I sub n. They're both equal to just A. All right, this is one of my favorite things. We'll be talking about this more in the next section or two. The matrix form of a system of linear equations is AX equals B, where A is the coefficient matrix whose rows correspond to the coefficients of the variables in the equations. X is the column matrix corresponding to the variables in the system. And B is the column matrix corresponding to the constants on the right-hand side of the equations. So for example, to write this system as a matrix equation, 4x minus 7y equals 9, and negative 3x plus 2y equals negative 5, it just looks like this. So your matrix A, your coefficient matrix, is 4, negative 7, negative 3, 2. Your column matrix X just has the variables X and Y. And the matrix B has the constants on the right-hand sides. Notice that the matrix multiplication does work for this. 4 times X plus negative 7 times Y gives you 4X minus 7Y. Negative 3 times X plus 2 times Y is negative 3X plus 2Y. So we're going to be talking about this more, as I said, in the next section or two. All right, for now, let's look at this application problem. A company has 3 appliance stores that sell washers, dryers, and ranges. Matrices W and R give the wholesale and retail prices of these items, respectively. Matrices N and D give the quantities of these items sold by the 3 stores in November and December, respectively. So we're going to do just a few parts of this problem. We will determine and interpret the matrices in parts A, D, I, and J. So let me switch over to the tablet. And here are those matrices again. So I'm just going to write myself a little note to remind myself that this stands for washers, dryers, and ranges. And then there was one other thing I wanted to check here. Okay, so in matrices N and D, the columns stand for stores 1, 2, and 3, and the rows stand for washers, dryers, and ranges. Okay, hopefully you can read that. Let's see. Okay. That is, let me do that again, because I don't think you can read that. If you can, it's only because I had already told you what it said. Sometimes this tablet is a little tricky. Okay, that's better. All right, so let's look at part A, where they wanted to know what is W times N, and then they wanted us to interpret it. So remember, this is washers, dryers, and ranges. It means that the wholesale price of a washer is $300, the wholesale price of a dryer is $250, and the wholesale price of a range is $450. Okay. So we're multiplying these two matrices. We have a 1 by 3 times a 3 by 3. So that operation is defined because this 3 and this 3 match. The answer will be a 1 by 3 matrix. All right. So let's see. The first row, first column will be this row times this column. So 300 times 30. Try to write that under here. 300 times 30 plus 250 times 20 plus 450 times 10. 300 times 30 is 9,000. 250 times 20 is 5,000, which is 14,000 plus 4,500 comes out to 18,500. Okay. So what would that number represent? Well, we took the wholesale prices of the washer, dryer, and range and multiplied it by a column that kind of stands for the inventory in store one, right? Let me just double check something here. The quantities of these items sold. Okay, so in November, store one sold 30 washers, 20 dryers, and 10 ranges. So this number, 18,500, stands for the cost to the company of the inventory that was sold in store one. Okay, so the other entries are going to give us the same information for store two and store three. So for store two, it'll be 300 times 40 plus 250 times 30 plus 450 times 5. And that comes out to 21,750. Okay, is the value of the inventory in store two. And now we do the same thing for store three. I'm just doing it on the calculator at this point. So 300 times 20 plus 250 times 10 plus 450 times 35 is 24,250. So again, this is what the company paid for the inventory that they sold at stores 1, 2, and 3. All right, next example is very similar. I would encourage you to pause the video and try this one yourself and then come back and compare notes. R times D. So again, it's a 1 by 3 times a 3 by 3. So the answer will be 1 by 3. The first entry will be 500 times 20 plus 450 times 30 plus 750 times 10, which comes out to 31,000. So this is the money that came in to store one for the inventory that was sold in December, right? In store one. So for store two, it's going to be 500 times 50 plus 450 times 10 plus 750 times 20, which comes out to 44,500. And then finally for store three, we have 500 times 30 plus 450 times 20 plus 750 times 30. All right, so store three had sales of 46,500. All right, that brings us to letter I. All right, letter I looks a little complicated. They want to know what is R minus W times N plus D. So I went ahead and figured out what is R minus W. This is R minus W. Matrix addition and subtraction is very easy, right? And this is N plus D. So what will this matrix represent? R minus W is retail minus wholesale. So that would be profit. Every time they sell a washer, they make a profit of $200. Every time they sell a dryer, same thing, $200. And every time they sell a range, they make $300 profit. And then N plus D is just the total number of units sold in the months of November and December. So this is going to give us the profit at stores 1, 2, and 3. Starting with store 1, that's going to be 200 times 50 plus 200 times 50 plus 300 times 20. Okay, so the profit at store 1 for the months of November and December was $26,000. At store 2, it was 200 times 90 plus 200 times 40 plus 300 times 25, which is 33,500. And then finally, store 3 is going to be 200 times 50 plus 200 times 30 plus 300 times 65, which is 35,500. All right, and lastly, we have part J, which is the easiest one. All right, they just want to know what is 0.95 R, and then we could talk about what that might represent. So you just multiply each of these entries by 0.95. Let's see if I can do this in my head. That's going to be 475. I think I can do 450, but I don't want to get it wrong. One of my favorite sayings is don't be a hero. If you have the calculator within reach, go ahead and use it. Okay, that comes out to 427.50. And then 0.95 times 750 is 712.50. Okay, so it's just 95% of the numbers in the revenue matrix. So for example, if they had a 5% off sale, these would be the new prices, right? If they normally sell washers, dryers, and ranges for $500, $450, and $750, and they mark them 5% off, now they're going to sell for $475, $427.50, and $712.50. All right, and that's pretty much going to do it for section 2.3. Let me just get my thing back here. All right, so if you would like to try one of these problems in the discussion, feel free to grab one of these. So what did we learn in this section? A matrix of size m by n has m rows and n columns. Matrices of the same size can be added or subtracted by adding or subtracting corresponding elements. The product of an m by n and an n by r matrix, I don't know why they switched to r now, is the m by r matrix whose ijth element is obtained by multiplying the ith row of the first matrix by the jth column of the second matrix. The product of each row and column is calculated as the sum of the products of successive entries. And that's going to do it for section 2.3. We'll see you next time.